Good morning, everyone. We are just waiting for more participants to join in, and then we'll be starting soon. Good afternoon, everyone. Welcome to today's session. My name is Ankita Sethi, and it gives me immense pleasure to welcome you all to one of its kind international webinar on expanding universe with radio telescopes and satellite, organized by none other than Golden Group of Institutions. GGI has been serving the society since 1960, brainchild of Sri Dinanath Mahajanji, and efficiently being managed under the leadership of Dr. Mohit Mahajan and Engineer Raghav Mahajan. It comprises of Golden College of Engineering and Technology, Golden College of Management and Technology, Golden Polytechnic College, Golden College of Education, Golden Senior Secondary School, Sri Nangli Academic Public School. Golden Group has been set with a clear mission to pursue excellence in the field of education and to adhere to the highest standards of academic region. In all its work, our academic philosophy revolves around the fact that practical knowledge and creative minds combined together can completely change economic and political destiny of the nation. And adhering to this philosophy only, we have not compromised with our ritual of providing quality education even during the pandemic. Number of competitions have been organized in the field of art and technology and other curricular and academics affairs. Placement and Training Cell has worked with the same zeal and conducted various placement drives online. We also hosted the 6th Mega Job Fair in partnership with Punjab government. We are the only institute in the entire region who have conducted more than 20 webinars on various social and technical issues. Before we get started, I just need to give you a little housekeeping. If you have any question during the presentation, please type them into the question box on your control panel. We will bring them at the end of webinar. अगर किसी को कोई भी question पूछना है, feel free to ask. You can write it in the chat box and we'll address those questions by the end of the webinar. Now I would like to hand over to our revered principal of Golden Institute of Engineering and Technology, Dr. Lakhvinder Singh, to just welcome our guest for today and also address all the participants who have joined us today for this session. Over to you, Lakhvinder, sir.
Yeah, thank you, Ankita. Am I audible?
Yes, sir.
Okay, thank you. A very good afternoon to one and all present over here. Myself, Dr. Lakhvinder Pal Singh, Principal, Golden College of Engineering and Technology, Gurdaspur, on the behalf of worthy management, faculty, staff, and students, extends a very warm welcome to Dr. Nikhil Gupta, Postdoctoral Fellow, School of Physics, University of Melbourne, Australia. Thank you so much, sir, for sparing your valuable time to deliver the webinar on the topic Expanding Universe with the radio telescopes and satellites. I also welcome our worthy chairman, sir, Dr. Mohit Mahajanji, MD, sir, Raga Mahajanji, and whole of the management of Golden Group of Institutes, Gurdaspur. I welcome all the guests and participants from various universities, colleges, schools, and institutes from all over India and abroad. It's indeed a great honor for all of us to have in midst of us Dr. Nikhil Gupta, sir. Dr. Nikhil Gupta is PhD in astrophysics, master degree in astrophysics, and bachelor's degree in physics. At present, he is serving as postdoctoral fellow in the School of Physics, University of Melbourne, Australia. He has published and presented enormous research papers in the reputed international journals, seminars, expert talks, and conferences. He is also working on various sponsored projects. I advise everyone present over here to take the maximum benefit from today's webinar. Uh, I also wish the today's event a grand success. I again welcome each and everyone present over here. Along with these few words, I close my speech. Thanks all. Over to Ankita.
Thank you so much, sir. Thank you for your words. Without any further ado, we will turn time over to our presenter for today, Dr. Nikhil Gupta. Let's get some inside secrets about radio telescopes and satellites from someone who is at present postdoctoral fellow at the School of Physics, University of Melbourne. He holds a PhD in astrophysics from Maximilian University, Germany, and has been a research intern at the University of Bonn. He has done masters in astrophysics and bachelor's in physics. He has published, submitted over 32 research papers, journals, and various international forums. Dr. Gupta has presented in various reputed seminars, conferences, research talks. Currently, he is also working on 6 projects, and the list of his achievements goes on. So at this time, I would like to invite our presenter, Dr. Nikhil Gupta, who is already with us, to please proceed the session and enlighten our students with your knowledge. Over to you, sir. Welcome to our session.
Hi everyone. Can you guys hear me? Can someone confirm?
Yes, you are completely audible.
Okay, thank you. So thanks a lot. Thank you for this embarrassing introduction as well. Um, so as I'll just share my screen first for presentation. That's something I want to talk about. Okay, so when I move the slides, you guys can see it moving. Oh, okay. I think it's a problem with the Zoom, so usually it works better with the PDF. Okay, this should work. All right. Thanks again for inviting me, and thanks for all the students and the alumni, principal of the college, and the managing director, as well as the other members of the college. Thank you for having me and asking me to present some of the work that we have been doing in the field of astrophysics. Um, so I'm gonna start. What? It it doesn't show. It doesn't move, or it's not changing the slides. Even with the PDF, it's stuck. Maybe I'll try to share it again. See, it works. Okay, now it's working. Okay, perfect. Sorry about this. So I'm gonna talk about some of the stuff that we've been working on, and very like a very general things. I promise I won't talk about any of the equations, or I won't show you any scary stuff. But I want to give, what I want to do is, like, I want to give you a very like a public view of how we see the universe in the research, and what kind of instruments we use in order to understand the expansion histories of the universe, various objects that we see up in the sky. And the talk title, I changed it a bit to like listening to the expansion of universe with radio. So what do I mean by this? Like, what does it even mean, listening to the expansion of universe, and that too with radio? So what I mean is, what does it mean by listening to the universe? So I mean, when we talk about radio or television, we are basically talking about, like, we want to listen to the music on the radio or watch some series or something else on television. So who actually, like, why do we listen to the universe? Who listens to the universe, and how do we do that? These are the kind of questions that I'm gonna talk about today. And also, like, when I was young, I used to think like telescopes as some instruments that you use to see probably moon or take very pretty pictures of stars or galaxies. But here I'm talking about radio telescopes, or the radios, in fact. So what kind of things that we actually hear from these radios or from the outer universe? So that's also something that I will talk about shortly. And then how do we like actually listen to the universe with these radio telescopes and the satellites? And wait, like what is actually the universe? Like why are we interested in universe? And we know that it's expanding now, it's a fact now. But what does it mean like for us that the universe is expanding? So these are some of the questions that I will talk about. And I will also like I see the number of students are here. So what I would also like, I will turn on the your mics at some point and ask you some questions so that we make it a little interactive, and I'm try to not make you sleep while I'm just talking here and you guys are just listening to me without like actual participating. So I think most of you know about the electromagnetic spectra, so the light waves, which is basically it's a frequency dependent phenomena. So what you see with your eyes is basically a visible eye. It's very small part of the electromagnetic spectra. There are many other things in the electromagnetic spectra, starting from the very high frequency gamma rays, which has like frequencies on the range of 10 to 25. And as the wavelength of light is inversely proportional to the frequency, so you have smaller wavelength for high frequency waves. And energy is basically your Planck constant times the frequency. So higher frequency means higher energy as well. Gamma rays are very, very high energetic radiations. So you have to like save yourself from gamma rays. You can't really expose yourself to the gamma rays. And luckily for Earth, where we live, our environment do that job, and we don't really have a very good exposure of the gamma rays coming from the universe. Other kind of evil rays are also X-rays. X-rays are used in medical examinations a lot, but it's not good when you have long exposures of the X-rays. So another good news is that our environment doesn't really allows the X-rays to permit through the various layers of the atmosphere. Then comes the ultraviolet light, and then this very small range of spectra which belongs to our normal visible light, which is the violet, indigo, blue, green. So normal light that you see with your eyes. And the way you see is basically the light is emitted by the object. So when you switch on the light in your room, the light is traveling everywhere, and whatever you're seeing is basically the light emitted by that object that comes to your eyes. That's how you see the visible light. But we humans are not really capable of seeing other forms of light in this electromagnetic spectra. So for example, we can't see X-rays. So thank God about that. We don't see that. It's very, very high energy photons. We don't see infrared, but these days you can find infrared goggles or night vision and stuff like that. Then comes the low energy or low frequency waves, which are the radar waves, which are used a lot in aviation industry, basically in order to see that which kind of objects in the sky are approaching, like aircrafts, or also in the army, that if an enemy is firing a missile or something. So you use this radar technology in order to basically get an idea that what is there in the sky. And similarly, just a little bit lower frequency is the microwaves, which are kind of the rays that are not heavily used in observing or doing the very industrial stuff. And they are there is a band which is available for the astronomers like me to basically observe the universe. And then comes the television waves. You guys have Data Sky or other kind of dishes at your home, which receives these television waves and that you see in the form of pictures in your television sets. Then the lower frequency ones are the radio waves, and then the very, very low frequency waves, which are the ELF waves. So here I'm talking about like usual telescopes. They are using the visible light in order to observe the universe, which are the optical telescopes, so doing several different optical surveys. But what I'm talking about is the radio wave here, which is basically used to listen to the radios, or like here I'm talking about listening to the universe with the telescopes, not the radios. So the technology is very similar, which is used in these big telescopes. It's similar to the technology which is used in these radios that you guys owned at some point of time in your life. I did. So there is a receiver in the in your radio which receives the radio waves emitted by some FM station, and that listen to the songs and anything you want. And then in the old beautiful times, there used to be these antennas on the top of roof of almost every household. And we have memories like people fixing the antenna and trying to get a picture on the television set. Like on the right here, a very old television that I think most of us, our grandfathers had such a television set at some point of time. So what if I tell you that, well, from this television set, you basically, what you're seeing is basically the universe. When there is no other signal, when there is no like DD National coming in the television, what you're seeing is a picture of the universe, which goes through your antennas, which are on the roof. And it shows as a very noisy thing on your television sets. I'll talk more about that, but I just wanted to give you an idea that that picture, a very noisy thing that you used to see on your television when there is no network or there is no connection, that was basically a picture of the universe that you used to see using this very small, very cheap telescope system with the antenna and very old television set at your homes. What we do with telescopes and satellites is basically it's much more efficient. The television, the dishes are much more larger. The receivers are kept at very low temperatures so that there is not much noise. And doing that, like for example, the telescopes in the space where you have very less atmospheric noise. That's why we basically fly the satellites, and then we can go to very like cold environments, like in the South Pole. The picture on the right is basically the South Pole telescope, which is a collaboration that I work on. So that telescope is in the South Pole where temperatures are very low, and you don't need much energy to make your receiver temperature even lower so that you get a less noisy picture of the universe using these amazing instruments. So these telescopes are big structures. For example, the picture on the left I'm showing is a 100-meter dish. So the antenna size is like 100 meters. That's huge, right? And this is one of the biggest telescopes, which is movable. You can also rotate it and make it up and down. It's an Effelsberg telescope in Bonn, Germany. But no matter, like, this dish size is 100-meter larger, but still this telescope is observing in radio regime in the electromagnetic spectra, which that is, it receives the radio waves. So the resolution of such a telescope, such a big telescope, is still equivalent to the resolution of our eye. So what we see with our eye, which is an amazing, amazing instrument that humans have, is a visible light. Like we see objects, we see stars up there, but with the radio telescopes, you see things that you can't see with your naked eyes. So that's why people are interested in building this big instruments in order to observe the universe, or as I say, in order to listen to the universe using these amazing instruments. But as I said, like the resolution is of the order of the resolution that uh, our eye has. So what do we like really can see in the like in the deep universe? With our eye, I can see some planets sometimes, maybe some stars if the night sky is clear, or sun, or I mean, few objects. Maybe if you're lucky or have a simple slowish telescope, you can see nearby galaxies with such a optical telescope. But you can't see very far away with such an instrument. So what scientists do is basically they collect several of these telescopes. For example, the top picture here is the GMRT telescope. It's a giant meter wave radio telescopes in Pune in India, which has like several dishes which are observing in the same region of sky. So since you have several dishes, it basically increases the resolution of the objects that you will see in the sky. Similarly, another telescope, and it's interferometric array in the picture on the bottom. So a basic idea of this interferometry is basically like, for example, you want to collect some water, rainy water for your cat or dog at your home. So what you do is like you put a vessel, and but vessel is not filling up very quickly. So you do another glass, or you put several objects to collect the water. So interferometry, for using these big structures, big telescopes, it also works in a very similar way. Like you have several telescopes, and in the picture here, as I show, if you have, for example, these 6 telescopes lying around in a circle like this, what these 6 telescopes will see or collect radio waves that it will collect from the sky is equivalent to the total area of this total area where these telescopes are placed. So that makes a huge area. And imagine you have telescopes in various continents. You have a telescope in Australia, in India, in America, and you're trying to see very same structures in the universe. So doing that, you collect a lot of photons, radio photons, and in that way, your resolutions improves a lot by doing this interferometry. So these are the things uh, that scientists basically use in order to observe the radio universe, in order to listen to the radio waves coming from the universe. But actually, like, what is it? Like, what is universe? Like, why are we interested in universe? Don't we have other stuff to do? Like, why do people do that? And why is it interesting? What do you see, like, when you look up in the sky? So I think that's something that I have a question from the audience as well. So what do you see when you look up in the sky? As I said, I'll try to make it a bit interactive. So maybe I will open the mics for some time. Okay, I don't know how to do that. Can someone do that for me? Some of the hosts. Oh, yes. So I basically want to ask this question from the audience, that what do you see up in the sky? I give a hint, you see moon, right? Maybe it's better that people can write down in the chat, and I'll pick it up. Like, you get some credits for that. What else do you see? You see planets, you see sun, right? What else do you see? Well, this all this stuff is like in the solar system, right? That's what you see with your naked eyes. But there are stars that you see, like very bright stars in different nebula, in different locations in the sky. And what you see is galaxies. Probably if you're lucky or you have a simplest of the telescope, you can see the closest galaxies to you, which is Andromeda. Well, not too close. I will come to that a bit later. What else do you see is galaxy clusters. So what are these objects and why are they so interesting? Why do we observe them, and what do we learn from these different objects that we see in the sky? So I'll just say a few things about these objects. Stars, you know, these are basically the stars are stars, right? So these are like sun, where helium is burning and it's producing tremendous amount of energy. Um, and there are billions of stars in the universe. And there are some places in the universe where these stars, they are attracted to each other gravitationally and they form galaxies. Like in this picture on the right, it's a Andromeda Galaxy, basically. It's a collection of stars, spiral arms, and there is a pulse in the center there. This blue region is basically identifies where the star formation is going on, and the inside of this galaxy, you see basically the old stars, which are reddish stars. And galaxy clusters are basically a collection of several galaxies. So these are the largest gravitationally bound objects that you have in the universe. These are the biggest systems that you see in the universe. And what they are is basically a collection of several galaxies. The range is basically in between 10 to thousands of galaxies, like in the picture on the left. It's an artistic picture, not a real one, but it shows several spiral or globular or different kind of galaxies that you have in a galaxy cluster. And on the right is a real picture from the Hubble Space Telescope. So it's a collection of several galaxies which form the galaxy clusters. Okay. So as I said, like, okay, all these structures are there up in the sky. We have telescopes, satellites, we're developing several things. We're trying to understand the universe. But looking at the structures, like at some point you see one galaxy, you take pictures of several galaxies, but what do you do with that? Why is it interesting? So I guess it's interesting because it's a way to look into one of the basic question that like haunts or that humans have throughout their life, that who are we and where do we come from? We live in a galaxy ourselves. The galaxy has the part of the galaxy which is the solar system. We have sun and planets, and our galaxy, the name of our galaxy is Milky Way. And how does Milky Way like form? Where did it come from, right? And how do these stars and several billions of other galaxies, where do they come from? And also these galaxies, they cluster together, they pull each other and form galaxy clusters. So how do these galaxy clusters form? So these are the very basic questions that we basically ask ourselves at some point of time, that what I'm doing here, like who am I live in a earth which is very, very small as compared to the whole universe. So how did this universe came into being? Like how did it form? How did it evolve? Where did it all started? Where did like somebody thought like I'd make a universe or what? Like how did it all became, and how we came into being here? So all these answers lies in the studies of the evolution of the universe, and the subject is known as cosmology. Uh, well, some people think of cosmology differently. For example, was a this advertisement in one of the American newspapers once upon a time, several years ago, where they wrote in the advertisement that make cosmology your career. What they wanted to do is train you, supervise in hairstyling, blow drying, permanent waves, coloring. Well, that's not cosmology. Cosmology is the study, it's a physics of the evolution of the universe. What they wanted to do was to advertise for cosmetology, but a lot of people make such these kind of mistakes. So our universe is expanding. That's what we know now from several observations of these galaxies, these galaxy clusters, and several other objects which I didn't talk about yet. But for example, stars, they also evolved. They were very younger in the beginning. They started forming these helium clouds cluster together. Then they started burning. And at some point of their time, when they are very, very old, they burst in the form of supernovas. I guess most of you have heard about the supernova, right? So also these kind of different objects in the universe that we study the properties of these objects, how far they are, what is the distance of these objects from the universe, from our Earth, where they are located in the universe, with what velocities they are traveling in the universe. So all this information helps, all these observations using several different telescopes helps us to make a picture of the universe. And then there are a group of people, there are huge groups of people in different universities who are doing simulations of the universe. That's basically you put some initial ingredients and you tell your computer, okay, this is my initial universe, and these are the laws of the physics, evolve and make a simulation and tell me like what will happen if I started a simulation at time 0 and what will happen after some time. And then you have these kind of simulations, you have models, you have theoretical work, you compare with the observations in order to understand the expansion history of the universe, that how we came into being, how we are living here in the Earth, but how did all the structure around us, our Milky Way galaxy and everything, how did it form? So that's the kind of questions that we ask every day, and we're trying to solve using these amazing like big telescopes and satellites, data coming from these instruments. So what is the expansion of the universe, and how do we basically know that the universe is expanding? It all started like almost 100 years ago when two of the very prominent scientists, American scientists, it's V. Slipher and Edwin Hubble, they were really, really interested in these newly developed technologies in the form of telescopes, and started looking up in the sky to different galaxies and different other objects in the sky. Uh, when what they observed is that basically, if our Earth is here, the galaxies around that Earth are going far away. And they did some measurement. They could, with the limited techniques they had, or limited uh, focal plane of the telescopes at that time, 100 years ago, they did it for some 40 galaxies and measured the distance versus velocity for these, and they find that it's a very pretty much linear, like when you fit a model to that, which basically means that these objects are going away from us. And later on, with the advance in technology, we got to know that it's not even that, it's not only expanding, it's accelerating. So accelerating is like you put an accelerator when you're driving a car, or you're biking or something, you increase the speed. So there is a speed with which these objects are going away from us, but it's not only that, they are accelerating away from us. And that's the picture of the expansion of the universe that we know today from the facts. I'll talk about briefly, like where did it all begin? How did we came into being, and what we see today? So I think many of you have heard about Big Bang Theory. So Big Bang Theory is basically a very popular name which is given to the lambda CDM theory, where lambda comes from the general relativity field equations from the Einstein. So Big Bang Theory, it all started with the Big Bang. Some people say the inflation comes before, or Big Bang comes after inflation, but it all started with a point, with a Big Bang. Something happened in the universe. I don't know, like there's not much information about that era. And it all started at time 0. so 10 to minus 44 seconds. Universe was very, very hot at that time. The temperature was like 10 to 32 kelvins. And the energy was also very, very high. Like all the particles around were very energetic particles. Then something happens, which is the inflation. That universe inflated very, very quickly into very large. It's actually one of the problem that scientists are still looking into, that whether inflation really happened or not. But the theories tell that if you want to solve several problems, then inflation is a fix, that inflation did happen. So the story of the universe is that, like, it started with the Big Bang, and there were several subatomic particles, cosmic waves, subatomic particles like quarks, gluons. There were electrons, protons, neutrinos, and a lot of radiation in the form of very, very hot cosmic rays. So all that were present in the form of a plasma, like a water in the sea, all moving together in the form of a plasma. And after 10 to minus 10 second, well, the universe was expanding even then, but it started a bit like the expansion was moving up. And at that time, slowly, as you move to the right in this plot, from left to right, the universe is expanding in this direction. And here we are. Here is what the observer is. Here is where the Earth is, on the very right panel, on the very right side of this plot. So in the beginning, everything was like in subatomic form. There were not even atoms. They were like pieces of the atoms, which are electrons, protons, and other subatomic particles. But as the universe was expanding, its temperature was decreasing. So as temperature was decreasing, its energy was decreasing. So what was happening, that these different subatomic particles, or the electron or the protons, they started combining with each other. And when these electron or the positron, or proton, they combine with each other, they form an atom, right? That's the hydrogen atom is basically a hydrogen is electron and a proton. When they combine together, they emit energy, they emit a light wave. So that's what was happening here, that the different electron protons were combining, forming atoms. Radiation was getting emitted, but then that radiation was colliding with other atoms, breaking it apart into electrons and protons, and so on. Like everywhere in the universe, that's what was happening. And the universe here, everywhere here, was in the form of the plasma. But soon, yes, the universe was expanding, temperature was further decreasing, it was getting colder and colder. So there was a time in the universe which is called the reionization era of the universe, where basically all the electrons, all the protons in the universe, they combined and they formed atoms, and there were no electron or protons left in the universe. And that basically emitted a lot of energy and a lot of radiation, which we call the cosmic microwave radiation. So if you're an engineer, if you will be working somewhere in the future, building telescopes, or I don't know, satellites in the future, or even if you are a physicist, and you'll be hearing a lot about the cosmic microwave radiation in your career later on. So it's like you ask people what you do, they are doing cosmic microwave radiation physics. So it's a big thing. It's a radiation which came from very, very early universe, when the universe was only 3 times 10 to 5 years old. And later on, as the universe was further expanding, it's 10 to 9 years, then 1.2 times 10 to 9 years, and the temperature was further decreasing. That this is the era when first stars started forming. And they all started forming from these atoms which were before this CMB era. So all these stars, they were colliding, they were coming together with each other, forming galaxies, the galaxies that you see here. And then you were the galaxies within themselves, they had their own ecosystem, which were making planets, a solar system where we live today. So that's the picture of the universe. That's what we know about the universe, or some part of it is a theory, and some part of that is well known now because we know the picture of the universe in this era. We see the galaxies with the telescopes, we see all that stuff with the optical telescopes. But why are radio telescopes useful? Because of this cosmic microwave radiation. So you cannot see this cosmic microwave radiation with optical telescopes, right? For doing that, you need radio telescopes. You need telescopes who can listen to this very energetic radiation at that time, like 3000 Kelvin temperature. It's like a lot of noise that you would listen only with the radio telescopes. So that discovery was like really important. This discovery of cosmic microwave background. And there are two physicists, Wilson and Penzias, who were given like a telescope from the Bell laboratories. So this is a very like a curious case of discovery of this cosmic microwave background, because before 1965, nobody expected that we will even like see this radiation at some point of time, because the technology was not so good. And also the theorists were not very comfortable that there will be such a radiation. And this radiation is basically coming from everywhere around us, from south, north, east, up and down. You have constantly still, you're receiving this cosmic microwave background radiation into us. Like, so the television that I showed in the beginning, it's basically what you see in this is a lot of noise, and it's basically the cosmic microwave radiation, which is coming from billions and billions of years away from us. So it happened billions of years ago, and we're still receiving this CMB radiation coming from that era of the early universe. So these two physicists were given this telescope by Bell Laboratories. They were not using this telescope anymore. So they asked them, okay, they wanted to use it to observe the universe, do something with that. And while doing that, they were hearing, or they were listening to this constant noise that you see in this TV, like basically here. But what they wanted to do was they wanted to hear something else. They wanted to hear those explosions, the supernova explosions, or they wanted to listen to the galaxies. They wanted to observe different other kind of structures. But well, they were constantly getting this kind of noise from this instrument. And they tried several things. They tried to insulate the telescope. Even they like thought that maybe there are pigeons in this structure, so they went in, cleaned the telescope, and did all kind of stuff. And in the later on, when they contacted other physicists in the different university who were doing the theory of this cosmic microwave background at that time, they found that it was not really a noise, but it's something physical. And these two guys were given Nobel Prize in 1978 for the discovery of cosmic microwave background. So this is how they actually discovered this very elusive radiation from the very early universe, and still you get away with the Nobel Prize. Well, so again, so I just talked about this plot, and so if you are an observer here, and you're very like a you're very poor observer, like I am very poor observer. You just have an antenna, and some guy like me who is not very expert in rotating the antennas and asking downstairs, did you get the signal or what? So with this kind of system, the radiation which is coming from the cosmic microwave background, with this antenna, you basically see this in your television. But what we use these radio telescopes and satellites for is basically you have this cosmic microwave radiation through these huge structures collecting a lot of radiation, and receivers are at very low temperatures, or for the satellites, they are away from the atmospheric pressure and very, very cold up there in the universe, uh, above the atmosphere. You see something better here, right? You see a picture, CMB basically. So all these fluctuations you see is CMB. But on top of that, you see these white dots here. So these white dots are basically the galaxies or the supernova or the AGNs that you start seeing when you use such huge structures. So you have very good resolution, you have less noise, and with the help of these telescopes, you see a better picture of the universe. So that's the whole idea of going from like a very simple receiver on the top of our roofs to these big structures, these telescopes, in order to see this very, very early radiation in the universe, which came in at like 3 times 10 to 5 years after the beginning of the universe. So billions of years ago, it was emitted, which we still receive, but we don't see a very good picture with a normal receiver. But with these telescopes, we see much better picture. And then you try to do several things. You use these objects to do the correlation functions, you do number counts, you try to compare them with the models, simulations of the universe, and get a better picture of the evolution of the universe. That basically we know that what happened here, we know what happened here, but we don't have a very good idea that what happened in the very, very beginning, like what's inflation, how did it happen, and what's a big bang, like how does all these things happen in the very beginning. That's like a fraction of scattering in the beginning of the universe. So using these satellites, for example, Planck satellite mission, which observed the whole sky of the with the satellite in the uh, 2010s. I think the mission is completed now, and this is the kind of the map that you see. For reference, this is the moon. So you don't really see much with Planck satellite. But when we go to the South Pole telescope, so this is a similar picture of the sky, similar part of the sky, but with a better instrument, with the South Pole telescope, which is located in the South Pole in Antarctica. You start to see these structures all these thing here, all these fluctuations are basically the cosmic microwave radiation. But on top of that, you have galaxies. So you start seeing galaxies when you go to less noise and you see a deeper picture of the universe. These white dots are basically the black holes. So I guess most of you have heard about black holes as well. These are basically the singularities in the universe, very, very dense structures, black, that these are so dense that even light cannot escape from these structures. So if you flash a torch to a black hole, the light won't come back. So you won't really see it, because everything you see is because the light is emitted back from that. You see that wall in front of me is because the light is emitted back from that wall. But black hole is something that even light doesn't come back. So you can't really see the black hole easily. But the way you see it, because all these stars or other gases around the black hole, which are falling in the black hole, and when they fall into the black hole, they emit immense amount of energy in the form of radiation in different frequencies. Like you can observe these in radio, like this map is a radio map. You can also observe them in optical, so in several different wavelengths. This is not the real picture. This one is the real picture of the black hole, which is done using the interferometry that I talked about in the beginning. That you have telescopes at different places on the Earth. You have a telescope in India, in Australia, in South Africa, and you combine the data from several different telescopes, in order to make the resolution better, much better than what you can see with your eye using these radio telescopes. So some people who predicted black holes exist, and one of them who actually helped observing using these different telescopes to observe this picture, this real picture of this black hole. They got the Nobel Prize this year. The people are basically Penrose and Gansel and Gaz, who got the Nobel Prize for predicting the black hole and observing the black hole in 2020. What else you see in that map is also these black dots. These are basically the galaxy clusters. So galaxy clusters are a collection of different galaxies. But in a radio map, you see them as a black dots, and they are very, very good observatories in order to study the high energy physics, in order to get understand the evolution of the universe. Because the reason these structures are there is because something happened in the very early universe. That's why these structures are there now. So these structures help you understand the evolution of the universe and ultimately help you understand that why we are here and how we are here. So the SPD collaboration is basically it's a South Pole telescope collaboration where there are something like 100 scientists, and half of them are postdocs and PhD students from 20 different institutions. The collaboration is like a worldwide collaboration. People from MIT, people from Berkeley, Fermilab, people from every country, from Germany, LMU, from University of Melbourne, myself. You can see here, I put a frame over me here. So these people are doing several different things. Some of these people helped developing the technology, building the receivers, telescopes, taking these telescopes to South Pole. Some people are still there who are living in the South Pole. And once you're there, you can't come back. So they are there for a whole year. And after a year, when it will be summer in the South Pole, then they'll be coming back. So all these people are doing something and to get the maps, to do the science, to fit the models, to do the simulations, and to bring together a collaboration and try to understand how the universe evolved and how we came into being. It's another picture of basically the Galaxy Cluster group meeting in Chicago. Their people are, most of them are Galaxy Cluster experts studying several things about the Galaxy clusters. So what these people, or what we are trying to solve, is some of the very important problems that basically what this universe is made up of. So in order to understand that how we came into being, how universe evolved, where did it started, we need to understand what it is made up of. So it seems that from the observations and several observations, it's confirmed that our universe that we see, like the galaxies, galaxy clusters, billions of objects, they only constitute 5% of the universe. So that includes photons, neutrinos, and black holes, a very, very small percentage of these. But all these structures, a lot of billions of structures, are just only 5%. And what is the rest of the matter is 25% of the matter, which is dark matter, which is dark. And we don't know what is it. We don't know like what are its properties. It's nothing like a visible matter, like the matter like chair or table. It's nothing like that. It's something else. The properties are not known, but we know that it's there in the universe. And it's like 5 times more than the normal matter, like the normal visible matter in the universe. So that's a puzzle that several physicists across the different groups, like from nuclear particle physicists and also the cosmologists, of course, they're trying to understand. And then very, very important part of the universe is dark energy. Dark energy forms the most of the universe. we don't know anything about dark energy. So it forms like 69% of the universe. And all we know is that it's around 69% of the universe. So what does dark energy do is basically it pushes objects away from us. As I said, the universe is expanding. So the universe is basically expanding because of dark energy, but we don't know what is it. We don't know what is dark energy. Well, it's just a name that is given to a phenomena that is expanding the structures away from each other, but we don't know what is dark energy. Other problems, more peculiar. I won't go into that right now, but it's basically the gravity waves which are coming from the very early universe right after the Big Bang. So that's also something which has been given a lot of attention in the scientific world. That well, something started with a Big Bang in the beginning, so it must have created some ripples in the space-time curvature of the universe. So that's something can be done with the telescopes like right now we have in the South Pole and other neighboring telescopes we have in the South Pole. So I will take it slow now. I think I'll just have a couple of more slides. But when you go back from listening to this talk, when you go back home or when you talk to your friends, I want you to go back with a takeaway that you learned about the telescopes. I guess you learned a little bit about the universe, how it expanded. It started with the Big Bang and what we see today. The television sets are basically observing the universe, but with the telescopes, you have better picture of the universe and you can do much more. But what I wanted you to take away from this talk is also something that a question that about the time machines. So it's a very, very fascinating subject, that the time machine, which are basically the instruments which can take you in the past. The instruments can take you in the future. So those are the time machines. They're very, very theoretical things. Nobody have even developed a very good theory to develop time machines. But how about I tell you guys now that there is a time machine in your eyes. So the eyes, the human eyes that you have right now, it's a time machine. So have you guys ever thought about, like, every time you look up in the sky, you are basically seeing the past? It's a very, very like fascinating that we don't realize it, but our eyes are basically time machines. We look up in the sky, we see the past. So how is that even possible? Interestingly, it's very simple. It's all because the speed of light is finite. Speed of light travels with a velocity of 3 times 10 to 8 meter per second, right? So that means we see our sun every day, but the light that sun has emitted, which we see, it was emitted 8 minutes ago. That means that light is 8 light minutes away from us, or it was in the past. It's very similar to like a lagging, like in the old telephone systems when someone used to speak, then there used to be some time lag that you actually receive what that other person has said on the telephone. But with this sun, which is very far away from us, like it's not a nearby object anyway in the solar system, but the time it takes for the sunlight to receive Earth is 8 light minutes. So every time we see the sun, we look up in the sun, we are looking at the past of the sun. So maybe at some point, like the sun is no more there, but we will still receive its light for 8 another minutes. And we wouldn't know that the sun is not there anymore because we are still seeing it for 8 more minutes. And imagine you look at a galaxy, like a nearest galaxy to us, Andromeda, which is 2.5 million light years away from us. So the light that Andromeda Galaxy, which is the nearest galaxy from the Earth, has emitted, it took 2.5 million light years to reach us. So imagine, like, maybe this galaxy is not there anymore. Like all the stars have died, they were all supernova explosion, and it's not there anymore. But we are still seeing the Andromeda Galaxy. But how do we see that? We basically see the past of that galaxy. And for the next 2.5 million light years, I don't know, some of you may be around, but I hope not, you will still see this Andromeda Galaxy, and then some point after 2.5 million light years, it will vanish. But maybe it's already not there. What you see is the past. So that's pretty fascinating. And now I guess all of you can go back and tell your friends and family that your eyes are basically the time machine. So the scientists don't need to look for the new time machines. So similarly, with these radio telescopes, what we are trying to do is looking into billions of years in the past to in order to understand the beginning of the universe, that how we came into being. All right, so that's all from me. Thanks a lot for listening. I have put a couple of links down here in this slide. It's one interview that I had with the website, the interview portal. It actually has a lot of interviews. So engineers and people working in different fields from India, and whoever has done something in their field, there is an interview there. So I think that's something you guys can have a look at how people develop their career. And if you are really more interested in this, you can have a look at my research articles in this link as well. So thanks a lot for listening, and have any questions regarding the talk or anything else.
Thank you, sir. Thank you for enlightening our students with your knowledge. It was a pleasure having you here. We had certain questions about time machine that have been beautifully answered by you. Yes, we can see the past. It is in our eyes only, and that has been beautifully answered by you. Then we had one more question. If sun explodes, what will happen? So if you could guide on that thing.
So for first thing first, like sun is not gonna explode in another 4 or 5 billion years. So you don't need to worry about that. But it's a very, very good question, that what will happen when sun explodes. Sun is basically it's fire. It's a lot of helium burning, a lot of fusion going on in the sun all the time. So imagine if the sun bursts, it's gonna burst in the form of a supernova, and this is going to destroy all the solar system, and it's going to push the earth and other planets and nearby stars probably outward in the direction out from the center of the solar system. So we won't be there to see that, which is good news. It's going to happen like 5 billion years after we die, but it's going to be a very, very big event.
Okay. Thank you, sir. And any other career counseling that you can do for our students? What courses they can opt for? What fields they can choose if they want to enter into this, sphere and universe? If they want to explore the universe, what all they can go for?
So I guess I didn't do anything like extra, or I was not a very brilliant student or intelligent student. What I did is basically followed my interests. I was interested in physics in the beginning, and later on I realized that there are amazing things that you can do in the astrophysics, and all this obsession with the sky, and uh, all these things like collecting the data, going to the telescopes to observe, looking at these objects, and then you get to know that this is all like a mature thing. Like, okay, you have a telescope, you take a picture of the universe, but that's not what an astrophysicist do. It's a lot of coding. So we have a lot of engineers in our groups also. It's a lot of coding. It's a lot of presentation, writing skills, a lot of that. So the way you want to proceed is very normal, like the thing that you're doing currently, and afterwards, if you want to go in that direction, You just need to look for a guidance, some guidance into your PhD, and from PhD you. I mean, for me it was basically the system. So I don't have a very good explanation that this is the way you want to go, but I would just say that it's your interest. So if you're interested in that, you will definitely do very well.
Okay, thank you so much, sir. Thank you. Again, we had one more question about artificial sun. If it is possible to make an artificial sun. So that was a question in chat box that I wanted you to answer, if this is possible.
I don't think making an artificial sun is possible for a human. But I mean, the sun is much bigger than Earth. So I'm not sure that you can build something bigger than the Earth while you are on the Earth. But also, we don't need another sun, right? We have enough sun. Well, one is good enough. It helps us doing everything we want. But yeah, I think it's not possible to make another sun, and we don't need one.
Exactly. Thank you, sir. Now I would like to invite our Managing Director, Engineer Raghav Mahajan, to present the vote of thanks. Over to you, Raghav, sir.
Thank you, Ankita. Am I audible?
Yes, sir.
Okay. Respected Chairman, sir, principals, teachers, Dr. Nikhil Gupta, and all my dear friends, very good morning. Very good afternoon to all of you. Today, I'm glad that we got an opportunity to listen to one of the eminent personalities in astrophysics, Dr. Nikhil Gupta from University of Melbourne, Australia. The way he described the facts regarding the galaxies, clusters, I think cosmology and the difference between cosmology, mostly the students are getting confused in that how the universe works, regarding the history of the universe, Big Bang. It was all amazing. I think that what we have listened today, I'm glad that we have a weekend ahead so that I can watch this video again and again to gain some more and more information regarding what you have shared today. Uh, Even I have a little bit knowledge regarding the universe, but I learned so many things regarding how the universe works, regarding the history that you have shared your experience. I hope all the students have gained same amount of information and they have gained so much knowledge from this webinar that they can use this thing to build their career in the future. One thing I would like to request to you, Dr. Nikhil, that whenever you will be visiting India, I wanted you to just visit our Group of Institution campus so that we can have a live webinar. We can't say webinar, live session for you, so that you can guide students in physically here. So मैं चाहता हूँ कि आप please एक बार visit करें इंडिया हमारे campuses में. So I wanted to invite you and I'm requesting you for that. So on behalf of whole Golden Group of Institutions, I'm very thankful for your valuable time and sharing your whole experience regarding the universe and radio telescopes. Again, thank you very much, Dr. Nikhil Gupta.
Thanks a lot for having me, and thank you everyone for listening. Thanks.
Thank you so much, sir. Thank you for a great session. It was really informative. Thank you so much. We thank you everybody for being with us today. We promise to organize such webinars for you in the coming days as well. And we expect the same enthusiasm from your side also. Thank you everybody for joining us. And hereby we are coming to the end for this session. Thank you.